Do I want to learn? And if the answer is yes, that means when you don't understand something, you ask. You have to ask if you don't understand something. I can't read your mind. I can only present the material and I can answer questions. I am happy to answer as many questions as you have, and I'm happy to go over stuff as much as you like, but you have to ask.
Is there an opportunity, a possibility?
You have to.
Is it possible that you can schedule the review sessions via Zoom so that like maybe more people can?
We can have a Zoom alternative. The problem with Zoom, I'm telling you from my experience, is that the level of that people catch things in Zoom is less than 1% of what they do in person. So if we can have sessions in Zoom, but from my experience, they're useless. They're absolutely useless.
But at least like more people can attend them, you know what I mean? Because I think Tuesday 5 p.m. not many people are around.
So maybe we can find another time that works better. As I said, I can do it on Zoom. I mean, I don't mind. The problem is, it's when you do it on Zoom, I have a piece of paper in front of me, and when I need to refer back to something on a previous page, it ends up being a mess because the camera doesn't have a whole blackboard on it. But more importantly, when people are on Zoom, and I had to teach for a year on Zoom, so I'm familiar with it. They're at home, there's noise going on, they get up and do other things, they're still logged in, they get up and do other things, and they don't pay attention. And even if they try to pay attention, people come in and bother them, and the atmosphere is not conducive to learning. Now, can I do it short? Will it be helpful? If that's what everyone wants, we'll do it by Zoom. But I think it's more effective if we find a time when people can show up and do it in person. But again, if everyone wants to do it on Zoom, I'll do it on Zoom. I'm just skeptical that it will help. Other questions? Okay, anyone who really got below here, I'm not convinced that they've caught on anything in the class. Anything. Zero. Because you can get 25 garbage points just by copying the problem, writing down the equation of the notes, and not solving anything. You know, if you can get into the mid-20s without really knowing how to solve any of the problems. Because I give you points for almost anything. Pretty much for copying the problem down, you can get almost like 8 or 9 points. You know, pretty much. So anyway, that's the my little bit of preaching here. I want you to learn the material. I want you, when you go and you're at your job and you have to do something with control, to impress your boss so that you get a raise, and not to depress your boss who wonders why she hired you at all. And it's not that hard. It's just a matter of when you don't understand something, ask. Ask and I will explain it. That's my job, is to explain it. And even if I have to explain it 10 times, I'll explain it 10 times because I want you to learn it. And I want you to do a good job when you get out and get a job. Okay? Okay, so are there any other questions on the first exam? I will give it back at the end of the class, otherwise people won't pay attention to the class. So this is the grade distribution, which by the way has much more information than just the mean and standard deviation. So the distribution is more meaningful than that. But even the top grades in the class really only did something sensible on 1.5 problems. Okay, so as we said last time, in the last class, up until the last class, we were observers. That is, we looked at systems and we tried to model them. And we tried to analyze those models. But we didn't do anything to the models. We didn't do anything to the system. We just observed them and tried to describe them. And the reason for that is, before you actually do something, control, you need to know how to model the system, because you're going to model the system and put control in that model. And you need to know how to do that analysis. So we spent a lot of time doing that. Now we're ready to do control. Control means we're going to a participant. We're not just an observer. And in control, we're going to, once we do control, we would like to have a few standard examples that we refer back to. So I want to just introduce two standard examples that when we do control, we'll refer back, we'll try to do them on these examples so you can see the difference between one situation and another. And so let's do A. A is, let's get this correct. So I have something flowing in with a certain V in, or V, and a certain temperature coming in. Since this is well mixed, I obviously have the theta coming out. And I can have a heat exchanger with a coolant, VC, velocity of the coolant. And obviously this is theta. That comes in. And so here I have a system. And what I'm going to do here is I want to have control. So with control, I would like to measure the temperature coming out. And if I don't like the temperature, I want to adjust VC. So the idea here is I measure theta, and I adjust VC. And I have a disturbance that's causing me problems in theta in. So I have a disturbance in theta in, therefore I get a different theta coming out from what I want. And I react to that by changing the cooling flow. So this we call the control variable. This we call the manipulated variable. And this we call the disturbance variable. That's just the notation that we've given in the past. So if we model this system, so this system has something in common with this problem. In this problem we did on the exam, two things change, not just one. Two inputs change. Obviously an output also changes, but due to the change in two inputs. So let's write this out. I've got rho V CV E theta V2. Okay, well I've got a theta in, so I've got rho V C E theta in minus theta. Theta in minus theta. And then I have plus UA times theta, the coolant, minus theta. Now, so this is of course in minus out due to flow. And this is of course in minus out due to the, or not in minus out, but it's the heat transfer from coolant. Now obviously if the coolant is a lower temperature than the temperature in the reactor, then this is negative and heat's going from the reactor to the coolant, which is typically the case. I just wanted to write it with, when I write a coolant, I wanted to write it with the UA. And we know from earlier in the semester that UA is the function of the velocity of the coolant, of the volumetric flow rate of the coolant. Because if I have laminar flow, then the temperature, there would be no mixing inside across a cross-section of the tube. So the fluid near the near the wall inside of the coolant would be warm, and the fluid in the center would still be cold. And so the driving force would not be that high for heat transfer. But if I have turbulence, then it gets all mixed up. So the temperature inside the coolant across the cross-section is uniform, and therefore lower than it would be than the temperature that would be near the wall otherwise. So I have a higher driving force for heat transfer. Okay, so now if I divide through by rho v CV. So I'm going to let CV equal to CP. And I'm going to divide through by rho v CV. And what I'm left with is d theta dt is equal to, well, the rho CP, so I have a 1 over tau times theta in minus theta. Because CV and CP are the same, and the rho's cancel, I just have a little v over big V. And then I have plus UA over rho v CV hat times theta C minus theta. And that, of course, is the exact equation. Now, let's take our pink chalk and figure out what's changing. Theta is changing, and I should be careful here. There should be little v over big V. And let's circle the things that are changing. Theta in is changing, V is constant. Since V is constant, but VC is not constant, so I was okay calling this 1 over tau. Theta in is changing, theta is clearly changing. Theta C is not changing, this is constant, but VC is changing, this is constant. And VC is in here. That thing is changing. So let's notice nothing nonlinear here, but this is nonlinear, this term. So I need to linearize that term. So let's linearize UA times theta, UA times theta. And this is a function, this is some function of VC and theta. So UA theta is equal to the derivative with respect to VC. Yes? You have to either speak slower or pull your mask down when you ask the question, so I can hear you. You pull your mask down, that's right. Okay, then talk slowly. Sure. Yeah, when you talk slowly, I can hear you. Okay, I circled the things that are changing. If VC changes, UA depends on VC, so this changes. Any change in theta in or in VC changes theta. So this is also changing. How do I know if a term is nonlinear? If either something is raised to a power or in some function, or if there are two pink things in the same term, more than one pink thing in the same term. So here there's only one pink in each term. Here there's only one pink in this term, this term. But here, these are multiplied, so they're the product of pink things, so they're nonlinear. So this is equal to DUA dVC at VC 0, the reference, times VC prime. Plus DUA theta d theta at the reference times theta prime. Well, this one's easy. DUA theta d theta is just UA. But this is more complicated because I need to know exactly the functional dependence of UA on VC, which in most problems that'll be given, but here I'm just going to leave it as a derivative. Okay, so now I rewrite the linearized equation for t greater than 0. And that's equal to d theta dt plus, and let's move things to the other side of the equation. So I've got plus theta over tau. So that's this term and this term. And I also need this term, which is the nonlinear term. So I move this to the other side of the equation, dua theta, d theta at the reference times theta prime. And then it's equal to what's left on the other side of the equation. Theta in over tau plus UA, of course I left out UA theta at the reference. So it's UA theta over rho V CV at the reference. That's this term. This term I've already written on this side of the equation. I still have this term. And I still have dUA theta dVC at the reference times VC prime. So now I'm taking care of this particular term, gave me 3 terms. 1, 2, 3, 1, 2, 3. This term is here, and these 2 terms are here. So that's linearized for t greater than 0. Now, as I told you, when you then do, now we have to do the t equals 0 before the difference. At t equals 0, you don't use the linearized one. You just make mistakes that way. You use the exact. Again, I said that, and a handful of people tried to make a mistake. You could do it with the linearized, but it's much easier to make a mistake. So people did it with the linearized and they made mistakes. Exact for t equals 0. That's d theta 0 over t plus theta 0 over t over tau. Now exact. Exact means I just rewrite this. 1 over tau theta in minus theta. So that's theta in over tau. And then I have this thing. So then I have UA theta over rho V CV at the reference times theta C minus theta at the reference. Theta C hasn't changed, and this is theta reference. Okay, and now I can subtract. So what do? I just copy this over, and I put reference here and reference there. And now I subtract. So when I subtract, I let prime, meaning t greater than something at t greater than 0, minus something at t equals 0. That's the definition of prime. So I look at the difference. This is d theta prime dt plus theta prime over tau. This is theta minus theta 0. And this thing just comes along for the ride. So I have minus dUA theta, d theta at the reference, times theta prime. With the reference as a t equals 0. And that's equal to. So I've taken the left side minus the left side. Now the right side. Theta in minus theta in 0 is theta in prime. Over tau. That's these 2 terms. Now, this, did I get my signs right? Yes, or no? I think I left out a term. So let's just check again. Let's make sure I didn't leave out a term. So I have this on the right. And then for this, I had UA over rho VCV theta C. I left that term out. There's a theta C. Theta C. That's correct. Okay, my mistake. When I copied over one of these terms, there's UA theta C over rho VCV. It's UA theta C over rho VCV. And at the reference. This is not the reference. Okay, so I have to fix that mistake, and let's go back and see how I fix that mistake. So let's just go back to this. So I've got d theta dt, that's this term. And now this term has two parts. I've got 1 over tau theta, and then I've got 1 over tau theta. So I've just taken care of this, this, and this from these three terms. So the only thing left is what's going on here. So let's look at this one. UA theta c over rho v c v, this term. That's UA theta c over rho v c v. So this check corresponds to that term. And now UA over rho v c v theta, that's the nonlinear term, that gets replaced by three terms. So the remaining term are these three terms. So let's see these three terms. I've got UA theta at the reference. So I've got UA, so I've got UA theta at the reference. So UA theta at the reference, rho v c v. That's this one. And now I've got the derivative at the reference, theta prime, with the plus on the right, so it comes back to the minus on the left. And then I've got this term, derivative with respect to vc, times vc prime. So the three terms here without checks are exactly these three terms. So I probably should have done that in 2 steps. It would have been more clear, but I think you can see now that the three terms without checks on it are exactly the three terms from the right-hand side. Okay, so now when we do the subtraction, we've done the left side subtraction, now we need to do the right-hand subtraction. So the right-hand subtraction, I did this minus this. So all I have is what's over here that's left. So I've got UA theta c, this thing at the ref, UA theta c of the rho v c v. This term cancels this term. And UA theta ref of the rho v c v, this term cancels this term. So what I have left is just one more term, and that's UA theta dvc at the reference times vc prime. Is that clear? So I want you to notice, and let's continue. Let's notice, let's let 1 over t equal 1 over tau minus the UA theta d theta at the reference. Now, as I'm sorry, is it theta or dc? Yeah. The UA theta, this thing is just UA. We said that's UA, so I don't have to belabor that. This is just UA at the moment. So here I get, and I'm not crazy about that sign. Yeah, I got that sign wrong. There was a minus sign here, so when it came to the other side of the equation, it had to come in with a plus sign. Why did I get that sign wrong? Because notice this whole thing, when it's multiplied by the theta, there's a minus sign on the right. So when I bring it to the left, I get it with a plus sign. So this is now a plus, not a minus. Again, let's review that. The UA theta c stays on the right with a plus sign. This guy, UA theta, with a minus sign, comes in with a minus sign. So I should have had these three terms subtracted. And when I bring the theta to the other side of the equation, I got it with a plus sign. I have a better idea. Let me just do it step by step and try to do it all at once. So I will do it step by step and just come up with it instead of having to backtrack. Let's just do it all step by step. Instead of trying to do multiple steps at once. That makes it less clear. Okay, so let's bring two terms to the other side of the equation. So I've got, so before I get here, I'm just going to rearrange this before I linearize. So let's rearrange. So I've got d theta dt plus theta over tau plus UA over rho v CV times theta. That's all on the right. And on the left, that's all on the left. Now on the right, I have theta in over tau. And the only term I have left is UA over rho v CV times theta c. So I've got plus UA over rho v CV times theta c. That's exact. And so you have to speak slowly into the mass. We'll see. Let's just see where the linear and non-linear terms are. So let's see what's changing, what's not changing. Theta changes, UA changes, theta changes, theta in changes, UA changes. So let's see what's nonlinear. This is linear, this is linear, this is linear, this is linear, this is nonlinear. Okay, so now let's plug in these three terms for this. Okay, so now I have d theta dt plus theta over tau. And this thing is going to be plus UA over rho v CV at the reference times theta. Let's see. Let's UA theta. So I've got UA at the reference times theta prime. That's this term. And the other two terms I'm going to move to the other side of the well, actually, I can leave one of those terms here. UA theta at the reference. And of course, I need the rho and the C. So I put both these terms in. And what's on the right is I have theta in over tau plus U plus UA rho v CV theta C. That's this. And the third term, I have, it has to come with a minus sign, dUA theta EVC at the reference times VC. Okay, so what did I do? I copied this term, I copied this term, I copied this term, and I copied this, and I copied this term. This term gives me three terms. One, this one is this one is this, and this one is this. I just plugged it in. Yeah.
Can you write down the last part of the computer? I cannot read the last part.
You can't read the last one.
The last bit, one of the last bit.
dUA theta VC at the reference times VC prime. I just copied this term divided by rho. I'm sorry, this term. dUA theta VC at the reference times VC prime. I just copied this term and divided by, and I have to, of course, divide by rho VC. Is that clear? Good question? Yeah. Okay, so this is the linearized. Linearized T greater than 0. and exact t equals 0. Exact. So the exact is at t equals 0. So I just copy this. The theta dt, theta reference dt, plus theta reference over tau, that's this term, is equal to theta in over tau, plus UA over rho v CV times A C, this is reference. And then I have minus, which I bring down the set equation, plus UA reference over rho v CV. So, and at the reference, and this is theta at the reference. U at times theta reference. Because it's all at t equals 0. And now let's subtract. And let's hopefully we haven't made any mistakes. So this is d theta prime dt. This is theta prime over tau. This is theta minus theta 1. This comes down on its own. Times theta prime. And now this term and this term are the same, because it's UA ref theta ref, UA ref theta ref over rho VCB. So this cancels. On the right, I've got theta in prime over tau. I've got, okay, and now I've got this guy so I've got plus UA prime, I've got theta C over rho v C. I'll deal with that in a second. And then I have a minus UA theta dVC at the reference over rho v C times C prime. And I seem to have one term too many, so, but most things look okay. So notice here I have the disturbance variable, and here I have the control variable. Control variable, disturbance variable. And let's just see what happened with this term, whether this thing belongs here. So this thing came from, I'm sorry?
You have theta in over tau on the right hand side for the linearized.
This?
Yeah.
What about
For the linearized,
yes?
you also have the exact.
Yes, that's how I got theta in prime over tau. This minus this gave me theta in prime over tau. Now I'm just looking at this term because I think there's a mistake in this term, so we might fix that mistake.
Professor,
So let's see where that one came from. That's
Professor?
okay. Let's just okay. UA. Okay, no, I see. So, this is actually UA, here I wrote it as UA prime over C, but UA isn't the independent variable, VC is. So I need to use the chain rule. This is the UA dVC, VC prime. So this is the same thing as dUA theta C, dVC at the reference, times VC prime. In which case, the right-hand side just becomes theta D prime over tau plus dVC of UA theta C minus theta at the reference times VC. And again, what we have here is just VC prime on the right and theta in prime on the right. So this is the disturbance variable, and this is the control variable. And now we can just let 1 over t be equal to 1 over tau plus UA at the reference divided by rho v CV. In which case, when I Laplace transform, so this thing becomes theta prime over t. And by the usual, when I Laplace transform, I just get theta prime tilde times 1 times s plus 1 over t is equal to theta in prime tilde over tau plus this thing, which I'm going to call alpha, plus alpha times VC prime tilde. And 1 plus st is just 1 plus st over t. So what we get here is theta prime tilde is equal to, so I multiply by t over 1 plus st. So I've got t over tau 1 plus st divided by underneath theta in prime tilde plus t alpha over tau times VC prime tilde. And here I have the Laplace transform of the equation. Yes?
I have a question about the exact line, the exact t equals to 0. In the right side.
I have a question about what?
Exact at t equals to 0. Right?
Yes. Yeah.
In the right side, that theta in over tau.
Yes.
Won't that cancel the theta in over tau from the linear?
No, because this is at the reference.
Okay.
Right, I needed to write that. Because everything at t is equal to 0 is a reference. Everything is a reference. So all the terms are the reference. Okay, so here we have the equation. And I want you to notice that the 1 plus st, the denominator, all came from the left side of the equation. It came from the system, not from the disturbances. This is the disturbance, this is the control variable, disturbance variable, control variable. The 1 plus st came from the system, not from the disturbance or the control, which is as usual. If I want to come up with the g tilde for how theta in prime changes theta prime, that's equal to t over tau 1 over 1 plus st. I just divided this out. And if I want the g tilde of how VC prime changes theta prime tilde, that's just equal to t over tau alpha. And let's remember what t over tau is. Well, we know we have an expression for t. So we know what t over tau is, and we can just get it directly from there. The other thing we can see is we can look at, well, actually, no, I think that's fine. I don't think I need to do anything else on that. Are there any questions on this problem?
Yes. And this, how did you go from this line to the other one?
How do I get this from the other one? You have to tell me what this is and what the other
When
one
you
is.
have d theta prime.
Okay, why don't we start with which line we're talking about? 1, 2, 3, 4, 5, 6, 7, 8, 9.
From 6 to 7. From 6 to 7.
1, 2, 3, 4, 5, 6. Okay, from here to here. Question, what's the question?
Yes. Can you go over again how do you go from line 6 to line 7?
How do I get from line 6 to line 7? Sure. So, first of all, I define 1 over t as 1 over tau plus this. So they're both multiplying theta prime. So the coefficient theta prime is just 1 over t, by definition. Now on the right-hand side over here, this term I just copied. And this term is how UA changes, the derivative of UA. But UA changes because of VC. So I use the chain rule. DUA, DVC, VC prime. So this just becomes DUA, DVC, or 1 over rho VCD, assuming 1 over rho VCD. It's how UA changes with respect to VC times VC prime. The theta C comes in as a constant, and the rho VCV comes in as a constant. So I just use the chain rule because UA changes by virtue of VC. And then, since both these terms have a VC prime in them, I just combine them. So I've got DVC, and again I need 1 over rho VCV. I have DVC of UA theta C, minus DVC of UA theta. So I just combine these two terms into this term.
Okay, and where did the d theta prime for dt go?
Where did d theta prime go?
In line 6. On the left side you have 2 terms like d.
Where did the derivative come from?
No, where does it go in the line 7?
I took the Laplace transform. Line 7 is just a continuation of this. This is just, again, the equal on the right-hand side. An equal, it's just continuation of what's going on in the previous line. Other questions? Okay, so that's this particular problem. Other questions on this? Okay, so the second canonical example will be 3 CSTRs in circuit. And I'm going to measure what comes out here. And let's notice that here I'm going to have a V in, and let's call this stream B, VB in, and XAB coming in here. And if I don't like that, I'm going to have a VA, XAA. So what's going to happen? I have some reactions going on in these reactors. And if I don't like what comes out, if I have the wrong concentration, then what I can do is I can adjust the flow rate of a second stream to spike the feed. So let's see what's going on here. So let's say I have disturbance is XAB. So I have disturbance to XA coming in here. And what I'm going to do is I'm going to have a manipulated variable. Is going to be VA. And the control variable is going to be XA3. So what comes out? XA3. The mole fraction of species A in 3. And of course here I have XA2, and here I have XA1. So I would like to, so again, I'm going to have 2 things changing. I'm going to have a disturbance variable XAB, and I'm going to have a control VA. And generally, to make this problem a little easier, we're going to assume that VB is much, much less than VA. Because XA, A is going to be much bigger than XAB. So the idea is, I have a low concentration stream coming in here, of A. And if it gets disturbed, I can correct it by just putting a little bit of XAA in, because this is much higher concentration. So XAA is a much higher concentration. And I don't need much of it, so VA is much, much less. VA, let's get this right. VA is much, much less, than VB. VB is much bigger. Okay, so let's write out the equations. The first equation is, let's calculate, so let me just write this over here, XAB. Let's calculate what the XA is over here. Because what happens here is a mixture of this guy and this guy. So let's call this XA in. It's just a combination of this string and this string. So that's equal to XAB times VB plus XAA times VA over VA plus VB. Because it's the mixture of this stream and this stream. So it's just their combination. Okay, so now we can write out the equations for the three reactors. So let's write out the equations for the three reactors. For each reactor, I have the XI, XAI, DT is equal to, and let's also assume that they're all the same volume. And that it's constant density. So that means they all have the same tau. So it's 1 over tau I times XAI minus 1 minus XAI. And then I have a reaction. So let's see which reaction we want to put in there. We want to make this a first order reaction. Yes, first order reaction. So minus K times, so I have to be careful here. We have CA is CA reference 1 minus X. This is the constant density system. So I should initially write it in terms of concentration. Well, let's initially write it in terms of concentration. CA. So this would be KCA. And let's just plug in terms of X. So I've got CA reference times minus the XAI dt is equal to 1 over tau I times CA reference times 1 minus XAI minus 1 minus 1 minus XAI. It's these two. Minus K CA reference 1 minus XAI. So here I'm just converting from concentrations to X's. Yeah?
Could you write a little bigger, please?
Sure.
Thank you.
So let's cancel the CA refs in every term. And let's cancel the 1s. And let's multiply by minus 1. So I get dXAI here. dXAI is equal to 1 over tau I. Now I multiply through by minus 1. So this one was a minus, becomes a plus. This one was a plus, becomes a minus. And now I have minus, and now I have plus K xai, and I have a minus 1 here. Should I have that minus 1? I'm not sure I have that minus 1, but let's just see. All right, well, we'll deal with that as necessary. We'll see if I need that minus 1 as it goes along. So let's just, and let's notice, and this is for I equals 1, 2, and 3. For all 3 reactors. Where I'm going, where XA 0 is XA in. Because what comes into the first reactor is XA in. And here is XA in. So let's just notice with XA in that XA in is a function of things that change. Let's see what changes. Things that change are what we said. Disturbance is XAB. This can change. And I manipulate VA. That can change and that can change. So let's notice that this is nonlinear because I've got a VA in the numerator and a VA in the denominator. So this is a function of XAB and VA. So I've got this guy in the numerator and this guy in the denominator. That ratio is nonlinear, and this ratio is nonlinear. So what I'm going to need is I'm going to need to write XA in when I linearize is going to be the XA in, well, it's going to be XA in at the reference plus the XA in dXAB at the reference times XAB time plus the XA in dVA at the reference times VA time. Is that clear? That's the linearization. I'm going to need that because for the first reactor, I'm going to have an XA in. XAI minus 1. So I'm going to need to linearize that because that's nonlinear. And I think all I have time for is to take these derivatives, or pretty much. So let's look at what this derivative is. The XA in, the XAB. Well, if I take the derivative of this with respect to XAB, there's no XAB here. I just get VB over VA plus VB. And this derivative is the XA in with respect to the VA. Well, I've got a VA here and a VA here. You may not like it, but we have to use the quotient rule. So if we use the quotient rule, we have the derivative of the numerator with respect to VA, that's just XA in, times the denominator, VA plus VB, minus the numerator, times the derivative of the denominator with respect to the VA, and that's just 1, over VA plus VB squared. So those are the partial derivatives, and under these assumptions, where VB is much, much bigger than VA, this is almost equal to 1, because VA is tiny compared with VB, so if I neglect it, I just get 1. And under the, let's just see what cancels here. Here I have XAAVA minus an XAAV. These terms cancel. And this gives me the VB factors out, VB times XAA minus XAV over VA plus VB squared. So, and now under the approximations, if VB is much bigger than VA, I can neglect the VA, and I have VB over VB squared just gives me a VB in the denominator. And if XAA is much bigger than XAB, I can neglect this with respect to this, and I have an XAA. So where we're going to end today is we have the general equations. We have have XA in, which is nonlinear, and we've used the linearization from the Taylor series, and we've calculated both this guy and this guy. And what we're going to do at the beginning of the next hour is we're going to take this we're going to solve this equation for all three reactors. Where in the first reactor, this is going to go in as the linearization for XA in, or XA 0. But all the others will just be what they are, and then we're just going to solve it. Are there any questions on